Hello students, in this video I am going to explain you Wheatstone Bridge. It is an arrangement of resistances in the form of a bridge by which the resistance of unknown conductor can be determined. Let us start. Wheatstone Bridge. See the circuit. This arrangement is termed as the bridge arrangement. Here four resistances are connected to form a parallelogram in which one of the diagonal consists of galvanometer, that is between B and D, and in the other diagonal, that is between A, C, the cell is connected along with key S1 and here the key is S2. The resistances are so adjusted that on passing the current, no deflection is shown in the galvanometer. This condition is termed as the balanced condition. Here the ratio of the resistances of the two adjacent arms of the bridge is equal to the ratio of the resistances of the remaining two adjacent arms. See here, at A the current passing through AB branch is I1 and the current passing through AD is I2. As in the balanced state, no current is flowing through the galvanometer. So, the entire current I1 will reach to Q. And here also the current I2 will entirely reach to X. Here X is the unknown resistance. Applying Kirchhoffs' second law in loop A, B, D, A. Let us draw the direction of the travel. From A to B there is one resistance P, so it will be termed as P times I1 as I have written here. There is no resistance in the arm BD. Then from D to A the direction of travel is against the direction of the current marked I2, so it will be minus of I2R. Let us equate it to 0. Now in loop B, C, D, B, let us draw the direction of the travel. It will be I1Q minus I2X because it is against the direction of the travel, so it will be minus equal to 0. That is equation number 2. Dividing equation 1 and 2, we will get P upon Q is equal to R upon X. That is, if P, Q and R are known, the value of the unknown resistance X can be calculated. And when the bridge is in the balanced state, then on interchanging the positions of galvanometer and cell, there is no effect on the balance of the bridge. So we can say that BD and AC are conjugate arms of the bridge. Now let us understand Wheatstone Bridge with the help of an example. Here we have to calculate the current from the battery. Let the current be represented as I. Let us see this complex circuit. It can be redrawn in a simplified manner. See this node, it consists of resistance R1, R2 and R5. See here, this node is drawn here consisting of R1 connected to the positive terminal of the battery, R5 connected to the negative terminal of the battery, and then a resistance R2. Now see this node. This node consists of R3 connected to the negative terminal. See, this is R3 connected to the negative terminal. This is the other node. R4 connected to the positive terminal. This is the R4 connected to the positive terminal, and R2 we have already placed. Let us see whether it follows the balanced state of a Wheatstone bridge or not. The balanced condition shows that R1 upon R4 should be equal to R5 upon R3. This we have searched and it is equal to 1 upon 2. That is, it is following the balanced condition. And if the bridge is balanced, no current will flow through this arm or through resistance R2. If no current is flowing, that means this resistance is not in the circuit. So we can draw this circuit in the simplified manner like this. That is, it consists of R1 and R5 in series and R4 and R3 again in series, because this arm does not exist now. So this will be the simplified formation of the bridge. Now look carefully, R1 and R5 are in series, so it will be equal to 3 ohm, and R4 and R3 are in series, it will be equal to 6 ohm. Now these two are actually in parallel. This combination and this combination are parallel to each other. The resultant can be calculated by the parallel formula like this. So the resistance comes out to be, total resistance or the equivalent resistance of the bridge combination is 2 ohm, and the current can be calculated simply by applying the Ohm's law. V is equal to IR. It will come out to be 2 amperes, which is the required answer. Now let us attempt one more numerical. Here in a Wheatstone bridge, 4 resistances are given. A galvanometer of 15 ohm resistance is connected across BD branch. Calculate the current flowing through the galvanometer if potential difference of 10 volt is applied across AC. That means we need to calculate the current flowing through this galvanometer. That means we need IG. Actually, if we look carefully, this is not the balanced state of the bridge. See, this is 100 upon 60 and this is 10 upon 5. So it is not the balanced state. So definitely current is going to flow through the RBD or through the galvanometer. Applying KVL in loop number 1, that is A, B, D, A, this loop. Let us draw the direction of travel. Let the direction of travel is represented like this. So applying KVL, it will be 100 times I1. Now this is the resistance of the galvanometer, so it will also be considered. It will be along the direction of the current is along the direction of the travel, so it will be plus 15 Ig. Here it is opposite to the direction of travel, so it will become minus 60 I2. See the KVL in second loop, that is in this loop. Let us again mark the direction of travel. Let the direction of travel be this. It is 10 times I1 minus Ig, as we are moving in the same direction as the direction of the current, so it will be positive. Here it is opposite to the direction of the current, so minus 5 times I2 plus Ig. Again through the galvanometer branch we are moving against the direction of the current, so it will be minus of 15 Ig. In the simplified form, this will be equation number 2. Now let us apply KVL in the bigger loop, that means this loop, that is we are considering the outer loop like this, and this will be the direction of travel. So in this it will be 100 times I1 plus 10 times I1 minus Ig, and negative terminal of the battery is striking first, so it will be minus of 10. In simplified form, this will be equation number 3. Now we have to solve equation number 1 and 2 to eliminate I2, because what we need is current flowing through the galvanometer. We have eliminated I2 from 1 and 2 and we have obtained this equation. Now equation number 3 and 4 are solved simultaneously in order to get the value of the current Ig. That comes out to be 4 upon 821, or simplified form it is 4.87 milliamperes. Thanks for watching. Please like, share and subscribe.